Hi everyone, it's Dr. Marks and our topic for today is descriptive statistics. Now I've divided this into parts, so this is part 1, which will be measures of central tendency and location. And the good news is you probably already know the bulk of this material, but still I would suggest that you pay attention because hopefully I'm adding just a little bit of new material to your knowledge base. So let's get started. First, in the last lectures, we've been talking about the first part of the definition of statistics. And so we've been focusing on data and data collection. But if you remember, that was just one element of the definition of statistics. Statistics also involves describing data. So that's where we are in this course. We need to learn about describing data. So part of the descriptive statistics category discussed in the introduction involves these measures of central tendency. So that's where we're going, descriptive statistics, which you're going to find is pretty easy content. As I've already mentioned, for just this lecture, we're going to focus on measures of location and measures of central tendency, and those are some fancy words, right? And you're familiar with these ideas, and in a minute you're going to be like, oh my gosh, okay, I totally know this. But in part 2, we're going to move on to measures of dispersion, and then we'll be adding on in a third part. So back to our definition. We've been defining statistics as the science of collecting, describing, and interpreting data. And as I said, we've been focusing on data collection. We've talked about data and data sets, but now we're talking about this middle portion of the definition, describing data. Now, when we talk about descriptive statistics, we need to make a key distinction, and that's between what is referred to as a parameter and what is referred to as a statistic, and these really aren't interchangeable concepts. So the reason we have to make this distinction is that we have different terminology when we're talking about populations and when we're talking about samples. And by now you definitely understand the difference between a population and a sample. Now, if we're discussing a population, then we need to use the term parameter. So a parameter refers to our population. So by definition, parameters are numbers that describe data for a population. So parameters go with populations, P and P, right? It's a little bit convenient there. So parameters are for populations. For example, if we were looking at the mean age of all professors in the United States, where all professors in the United States is our population, right? A population that's probably too big to collect data on, then that mean is a parameter. However, if we're discussing a sample, which we all understand is a subset of the population that hopefully we've collected randomly or in some method that doesn't involve selection bias, but when we're talking about a sample, we use the term statistic. So, sample and statistics. Statistics are numbers that describe data from a sample. And so I love how that lines up, parameters for populations and statistics for samples, P and P and S. So it's kind of silly, but those kinds of things might help you remember. So an example, back to our professors, we've just said that our population is all professors in the United States, but what if we look at the mean age of our sample of 2,000 professors? Because we've already said, hey, collecting data on age of all professors is difficult. We're going to take a sample of 2,000. When I calculate the mean for just that sample of 2,000 professors, now I have a statistic. So parameters versus statistics. Now, the most basic descriptive statistics that we can cover are these measures of central tendency. And as I said, that's a really fancy name for something you already understand. These are also called measures of location. So measures of central tendency are the same thing as measures of location. Two fancy names. But most commonly, we refer to these as mean, and we're going to use the arithmetic mean, the median, and the mode. So guys, how easy is this, right? We've all been doing means, medians, and modes since somewhere in middle school, am I right? So there's nothing confusing about this. As fancy as those terms sound, measures of central tendency, measures of location, we're talking about some very basic descriptive statistics. I know you already understand that a mean is an average, and that a median is the middle observation, and the mode is the most frequent observation. So guys, the content in this class is not going to get any easier than this right here. So let's just look at a very simple example. And I know you guys could do this with your eyes closed, but I've given you some data and we're looking at number of weeks 1 through 10 and the number of new clients that our company brought in each week. And so let's start with that mean, and we're going to use the arithmetic mean. And of course, that's just the average. And I know you know how to calculate the average, but if I asked you to put it into an equation form, you should be able to. So I know you know how to do it, but could you write out the equation? Well, sure. It's simply the sum of all of the observations. So I need to add 42 and 56 and 43 and 51 and 47, 47, 55, 50, 49, 52. You get that idea? I need to add all that data in the column and then divide by n, the number of observations. And since I have 10 weeks, I clearly have an n of 10. So my sum turns out to be 492 new clients brought in over this entire 10-week period. When I divide it by 10 weeks, I average 49.2 new clients per week. So that's my arithmetic mean. Super easy, and I know you know how to do that already. Now, when we talk about the means, we need to use different notation when we're looking at a population versus a sample. So let's start with the population here on the left. We actually refer to it using this Greek symbol, which is mu. So when we're talking about population means, we're talking about some value for mu. And again, how do I calculate mu? Well, it's the sum of all the values. So you see there the summation of x divided by n. So in the second row, you see our simple equation where n is the number of values in the population. We practiced the same kind of calculation just a second ago. But remember, this is called a parameter. So a parameter of the population. Mu is a parameter of the population. For example, if we calculated or collected test scores for all students at a school, that might be our population, and I could calculate the population mean, again indicated by mu. But if we're talking about a sample instead, we use slightly different notation, and our sample mean is x bar. So you see x with that bar over the top of it, that's called x bar. So how do we calculate x bar? Well, it's really the same calculation, right? So you see the sum of x divided by little n. So we used capital N for number of values in the population, but here we're using little n for number of values in the sample. But again, isn't it the same calculation? It certainly is. And in this case, as we've already noted, since we're working with a sample, this mean x bar would be called a statistic. So x bar, our mean of the sample, is a statistic. So what would be an example? Well, what if instead of looking at all test scores for students, I looked at test scores for a random subset of students? That would be my sample. So again, you get the idea. Measure of central tendency, the mean, is pretty basic. Now, one thing I want to point out is that means do provide useful information. I mean, think how many times you've been reported the mean of something, right? Means, as simple as they are very useful. But at the same time, we want to have a more intuitive understanding of these central tendency measures. And we need to appreciate that means can also be limiting. Because while means are useful, they tell us nothing about the spread of the observations. So are they spread really wide, or are they kind of tightly grouped? We don't know, and the mean doesn't help us learn that. So it's really important that we be careful about what we can and cannot learn from a mean. And even though you're going to be doing some very basic things, why maybe calculating mean for some data as part of a project, I might ask you to tell me what that mean does and does not tell your client. So we want to be able to articulate carefully. One example that I want to show you is with respect to gross domestic product figures, GDP. And so it's true that the mean is useful, but it's also not going to tell me the whole story. So I've pulled some GDP data for two countries, the United States and China, and these are both very, very large economies. And so when I look at this data, both of these countries look like they're rich, right? I mean, they both have really large GDPs, $20 trillion and $14 trillion, making them, I believe, the first and second largest economies in the world. All right, so how might mean be useful? Well, right now these countries look similar, but what if I calculate a mean? So what kind of mean might I be interested in? Well, what if we calculated GDP per person, which is a kind of a way of estimating income per person. So if I take these two measures of GDP and divide through by population, I'm essentially just taking a mean. Well, when I take that mean, all of a sudden, these two countries look very different. GDP per person, the mean GDP is $63 something thousand for the United States, but is only $10,000 something for China. All right, now we're starting to see that by calculating some averages, it means we learn very different information. So this is just a simple example where I calculated GDP per capita, which I said is a measure of income per person. And we see now a very striking difference between the United States and China. So that mean can be very helpful. But here's the thing. I can't learn anything from this data other than for the average person. The average person in the United States has an income approximated by GDP per capita of $63,142, and the average person in China has an income approximated by GDP per capita of $10,411. But I don't know much else other than that. For example, what about people who are not the average person? What can I learn about the spread of the income? Is the income distribution super wide or is it narrow? Well, as you understand, mean doesn't help me answer that question. So again, be careful to articulate carefully what can a mean tell us and what can a mean not tell us. Now, obviously, we're going to be combining means with other descriptive statistics for a fuller picture. So, we'll return to this idea in part 2 where we want to get a sense of dispersion. Are things more equal? Are they more unequal? So we'll come back to that idea. Now here's an example that illustrates this as well. Let's say that you evaluate job satisfaction ratings for 3 groups of workers at your firm. These could be different departments. It could be people with little experience, medium levels of experience, and lots of experience, or seniority at your company, people that are new, people that are, not that new, and people that have been there a long time. Whatever. You can think of 3 distinct groups. And do you agree here that all 3 groups have the same mean? So if somebody from HR was simply to report to me mean level of satisfaction, and we see that kind of thing all the time, right? We're provided means. Well, would that be enough information for you to really understand what's going on? And the answer is no, because while these 3 groups have the same mean level of satisfaction, they have very different standard deviations, which refers to the spread. And we'll define that better later. But look at the blue group. Now, the blue group has a high level of satisfaction at 50. Well, I'm assuming that's high. But it's pretty tight. So whether it's high or not, people don't have huge differences in opinions. But now look at the green group. Something interesting is going on there. They have the same mean as the blue group, but gosh, you've got some people way into the left tail and way into the high tail. So some people are highly unsatisfied with their jobs, right? And some people are highly satisfied. And so if this was data that you had at your disposal and you knew something more than just the mean, you could probably get to the bottom of this. I'm guessing that while you might feel that you don't need to do a whole lot of intervening with the blue group. You might want to get to the bottom of what's going on in this green group, right? Because something clearly has gone awry to have such different ratings on satisfaction. Means can be skewed by extreme observations. So what if you have a data set with some extreme observations in the tails? Well, that can certainly impact your mean. So you want to look and get a sense of whether or not you have an outlier or a set of outliers. So what do we mean by outliers? Outliers are data points that differ significantly from other observations. So maybe when you're plotting your data, you see a kind of a reasonable distribution, but then you've got an observation that's kind of way out there. And certainly that can influence your measures of central tendency. So what if we have an outlier in our data set? For example, maybe you've been charged with doing something related to employee salary data, and that data set includes the CEO. And it could turn out that that CEO makes so much more than anybody else. Well, if I leave that CEO in, an outlier, then it's going to impact my mean. So sometimes we have to decide, does it make sense to eliminate outliers? Do I get a truer picture? Maybe I want to report with and without the outliers just to cover myself. Or maybe you work for a retail entity and you've got data on daily sales, and that data includes Black Friday. Likely Black Friday could be an outlier if you're a retail entity that people go to visit. So if you're a store in a shopping mall, Black Friday could be an outlier with respect to your sales data. So again, do you just average that in, or do you take it out? Do you report both kinds of data so that people can form their own conclusion? Either way, we do need to appreciate the existence of outliers can distort the mean. And so you want to think carefully and critically about how you're going to treat data when you have outliers. Again, if I report the mean with the outlier, it could make it harder to learn from the mean. So it's a judgment call here. Outliers can cause problems in other statistical measures and techniques too. So this idea of outliers will come up again. Means aren't the only way that outliers can influence your analysis. So let's look at the same data. 10 weeks, how many new clients did we get in a week? And now we're looking for the median this time. So we're done with mean. We want to now find our median. Now remember, our median is our middle observation. And if I'm looking for our middle observation, then I need to put this data first in sorted order. Now in this example, it's easy to eyeball because I've only got 10 observations, but I could have a large data set, right? So it's easy to eyeball unless we have a whole lot of data. And then we probably want to ask Excel to do this for us. So if I sort our data, which we've done in Excel, we can see that our median kind of falls between 49 and 50. I have an even number of observations with 10, and I did that on purpose, so I don't have a median that just jumps out at me there. So what do? Well, since there's no actual middle, we're going to have to average the two observations. So if I had an odd number of observations, then I could find that median easily, but in this case, I have to take the average. So clearly the average of 49 and 50 is going to be 49 and a half. But again, just like with the mean, this median tells us nothing about the spread of our data. So I don't know if there are some weeks with very few new clients or some weeks with just huge number of new clients. It only tells me about that middle point. Now the mode, as we've talked about, is the most frequent observation. And there doesn't actually have to be a mode at all, right? it's possible that I have no repeating observations. And if I have no repeating observations, then I'm not going to have a mode, right? So we could have a mode or we might not have a mode. But in this case, it's pretty clear that our mode is 47. 47 is the only repeating observation in this data set right there. Now, measures of central tendency can help us understand another idea, which is called skewness. So we've talked about, again, 3 measures of central tendency: our mean, our median, and our mode, and we can use those to help understand skewness. And what do we mean by skewness? We're talking about when our distribution skews or points to the left or to the right. I'm going to show you pictures in a second. So we can help get a sense from our measures of central tendency if we have skewness, where we have observations pointing to the left or pointing to the right. And so this means that we're going to have these tails of our distribution. So if I'm able to look at my distribution, then I can tell from these tails if I have skewness to the left or skewness to the right. For example, look at these 2 distributions. They're not symmetric, right? Neither of these 2 distributions is symmetric. If I look at the left distribution, do you see that tail that's going to the left? So I would call that having negative skew. Don't confuse this, because do you agree this distribution on the left kind of looks like it's pointing a little bit at the tip to the right, but that's not what we're talking about. We're talking about the tail that's going to the left. Whereas on the right side, we see positive skew because we have a tail that is going out to the right. So our negative skew, we have a tail going towards negative observations, although I don't have any actual negative observations. On the right, we have a tail going towards positive observations. Now, in this example right here, we have a symmetric distribution, right? And by symmetric, we understand that if I were to kind of fold it on that middle, the left side and the right side totally align, right? What's on the left is identical to what's on the right in terms of the distribution. So in a symmetric distribution, what we see is that the mean is equal to the median, which is equal to the mode. So all 3 of these measures of descriptive statistics for location or central tendency are all going to be the same. And in this example, we don't have any skewness, right? We don't have a tail going out to the left, but not the right. There's no tail going out to the right, but not the left, right? No skewness here at all. So we would say that we have a symmetric distribution, and by definition, symmetry means mean equals median equals mode, and we do not have any skewness. However, the distribution we just looked at right here is on the left, but let's look at the one on the right where we see a distribution that is positively skewed, right? So we know this is positively skewed because that tail is going off to the right. And what we see here is that the mode and the median and the mean are no longer stacked on top of each other. They're no longer identical. But the mode is easy to determine, right? Because remember, the mode is the most frequent value. So it kind of makes sense that that hump is where we see the mode. But here's the thing. Those observations in that tail, which goes to the right, well, those observations in that skewed tail are pulling up the mean and they're pulling up the median. So that is why all of a sudden the median gets pulled up, the mean gets pulled up, and they are no longer equal to the mode. Now we can see the same thing if we look at a distribution that is negatively skewed. So look at the distribution on the left and you see that tail going towards the negative right? So that's a negatively skewed distribution. And once again, as the node at the top reminds you, the mode is the most frequent value. So that hump, again, makes sense where the mode is. But now look what's happened to the median and the mean. They're being pulled down. So the observations in the tail pull both that mean and that median down. So when we're looking at a skewed distribution, which is going to be more impacted by observations in that tail, right? Those skewed observations that go far off to the left, which is going to be more impacted by that, the mean or the median? So think about that for a second. In a distribution, so you have a set of data and you have data that's skewed to the left. Is that going to influence the mean or the median more relative to a symmetric distribution? Well, if you decided it would affect the mean more, you'd be correct. So skewness is more likely to affect the mean more than the median. So if this is the case, when you have skewed data, the median might be a better measure of central tendency. It might actually be better than the mean. Now, would it make sense to report both? Absolutely. But which one would you rely on more if you were trying to get a measure of central tendency? If you were trying to describe our central tendency measure, well, median might be more useful. And that's why sometimes you see medians reported instead of mean. Again, it depends on what you're trying to convey, and it also depends on what you think your distribution looks like. And if you think it's not symmetric and it is skewed, then median could be very useful. So let's recap really quickly. We've been talking about the most basic descriptive statistics, which are these measures of location or central tendency. And the most common ones are the mean, median, and mode. Again, something I know you're already familiar with. And these can be helpful, but they can also be very misleading. So think about how many times you've seen a report give a mean, and you want to say, okay, but wait a minute, that doesn't really tell me very much information. So means, medians, and modes can be misleading if we try to make conclusions from them because they don't tell us that much about our data set. And one thing they don't tell us is about the distribution. So how skewed, how wide is the distribution? Is it tightly grouped? Is it not tightly grouped? And again, measures of central tendency tell me nothing. So we have to be careful about what we can and cannot learn from these measures, and we have to be careful about what we communicate and what we conclude in relation to these measures. So in part 2 of our unit on descriptive statistics, we're going to address these measures of dispersion, because when we combine measures of dispersion with our measures of central tendency, now we can tell a much better story. It's certainly going to add information about what our data looks like. And so measures of dispersion are things you're also familiar with: range and percentiles, standard deviation, variance. So that will be our topic for part 2. As always, thanks for viewing. If you have any questions, let me know, and I hope you have a fantastic day.